Thank you very much. So thanks a lot for this very nice introduction. So let's say in this presentation, my aim is really to introduce somehow those 2 days, because we are moving from the attention from the data towards building applications on regional climate projections. So mostly we focus on their views, on the challenges and the solutions that are proposed for specific use. And somehow I will mention only examples without going into the details, because you will have much more details after my presentation and in the next days. Okay, so this slide is the same slide that Carlo presented on day 1. And actually, this shows the links between the observations and the model data that are on the left-hand side of this slide to the users that now appear on the right-hand side of the slide, so a different typology of users. So we have legislators, business, citizens, and somehow those users need kilobytes of information to manage the climate risk. And let's say the step further is really that the service is not only providing data to the users, but it is providing evaluated and quality control, best practices. It is offering user support, training. And at the center of this slide, you may see the climate data store that has been presented as this one-stop shop where data and information are collected. And I would like to highlight that based on the nice discussions that happened in the other webinars, together with the data, we have a tool or a software infrastructure that permits to operate and process the data. So what I'm going to introduce here is based on the C3S information that is relevant for different sectors. So here we are mentioning sectors that are vulnerable to climate change, sectors that were, climate actionable, so where somehow we need to adapt. So adapting to climate change means taking action, of course, means preparing and adjusting to the effect of the climate change, the current climate change, but also the projected one in the future. So the regional projections are among the most used data for the sectoral information. And the blue sectors that you see highlighted in my slide are, the focus of the next presentations today and in the next webinar. So in this slide, I would like somehow to put some, or to highlight some cross-cutting themes and some challenges that we have to deal with when looking at climate projections. And the first point I mentioned is related to the uncertainty. So somehow we will have different ways of dealing with uncertainty. The second point I would like to mention is the bias correction. So different methods are offered and somehow those depend on the application themselves. I will add one word about the use of the regional simulations with respect to the global simulations. Somehow global projections can be, of course, downscaled with both regional climate models, so through a dynamical downscaling, but also with statistical downscaling methods directly on the global simulations. In many sectors and in many applications, we have to deal with extreme events. So the information about the extreme is really important. And we have learned in the previous webinars how dealing, with the higher resolution in space and in time data that climate projections offer is really important. The next point that I would like to mention is the concept that's behind the sectoral information, that is the co-design of the information together with the user. And this is, of course, an important challenge. Now, if we focus a bit on the uncertainty, let's say uncertainties in the future projections comes from different sources. And of course, they are introduced at different levels and at different stages in the modeling process, in the modeling chain. For example, we are dealing with the forcing uncertainties. And those are, if you remember, we have had this very nice presentation by Olivier Boucher, also highlighting the different, those different forcing scenarios, which one may be considered the more realistic and which ones are a bit of the less realistic ones. And somehow, when we have to deal with the forcing, the uncertainty associated to the forcing, this may be circumvented by focusing on specific set of projections, for example. The second source of uncertainty I'm mentioning here is related to the initial and boundary conditions. But as we are dealing with climate projections, these are of minor importance. let's say that the most important contribution to the uncertainty is related to the fact that climate models are imperfect and that the projections are uncertain. This specific source of uncertainty may be subdivided in three typologies. So first, we have an uncertainty because we have a limited theoretical understanding behind some processes. For example, we may have a limited knowledge about how aerosols are affecting the cloud formation. Or then we have an uncertainty related to the model parameters. So we have to introduce parameterization because there are processes that our models are not able to resolve. And somehow the fact is that the large scale effects of those parameterization then are somehow described in an empirical way more than resolved. And this is leading to an important source of uncertainty. And last, we have a structural model uncertainty. So this is also known as a kind of a model inadequacy. So this means in practice that there are no set of parameters that can make the model agree with the observations. And this is happening because maybe certain processes are not represented, not fully represented, they are missing, they are just approximated. Here I've shown a quick example, but there are of course an infinite number of examples in this respect. And on the x-axis, you see of this scatter plot the representation of the cooling in the stratosphere associated to the ozone depletion in the southern hemisphere. And on the y-axis, you see the shift, the polar shift in the tropospheric jet that is happening during summertime in the southern hemisphere. And somehow in the small points are all the CIMIC models and how they are able to represent those connections. Let's say that the models that do not have a good representation of the stratosphere, they are unable to fully represent those kind of connections. And this is somehow was based on a choice of the different modeling groups related to how the stratosphere has to be represented in those kinds of exercise. Now, what I would like to focus here are more the consequences of underestimating the uncertainty. And when we have to deal with an ensemble of simulations, there are important impacts or repercussions on the fact that simulations are used then as input to impact models are not fully spanning the uncertainty. And there are again several examples that many studies look at the effects of selecting, for example, regional models for impact simulations. And here I was just quickly focusing on one example that focuses on a completely different area, that is the biodiversity. This is an example for the biodiversity loss modeling. So these kind of bars represent the uncertainty that is associated to different components of those kind of simulations. So in blue, you have the uncertainty that is associated to the choice of the different scenarios. Whereas in purple, you have the uncertainty that is associated to the different choice of the model, so the species distribution models. And finally, in orange, you have the effect of the choice of the different general circulation models that are chosen, and all are contributing to the uncertainty. So one important point here is the fact that one way to study the uncertainty is the fact that we consider results from multiple models. And this is what we offer at C3S. So at C3S, we provide or we offer solutions that are based on multimodal approach. And this because the multimodal approach provides a sensitivity test to the model's structural choices. It is based on the assumptions that multiple models provide more reliable information than a single model. Of course, it depends on the application, to be honest. And finally, that we have higher confidence on results that are common to an ensemble, even if we have to consider the fact that all models can suffer from similar kind of errors. Finally, given that we are dealing with applications and often we are dealing with non-experts, for the non-experts, the collection of results is often much more useful than and needs to be combined and synthesized in some way. Now, let's say the question is how how model trust can be increased by combining results coming from different models. And here, of course, we are talking about a lot of possible multiple dimensions that were discussed also in the previous webinar, such, for example, the model skills, or covering the spread of the ensemble, or the independence of the model themselves. So not considering two similar models in our multimodal compositions. Or again, considering the spread in the model climate sensitivity, or the skills of the model for specific processes or local skills. And I'm going to showcase a couple of examples, and different strategies. This is one of the first examples is related to our operational energy activity. The background information is that, of course, the energy sector is increasingly relying on renewable resources. And so the climate variability and climate change information becomes always much more relevant. And so we need to give to providers and to policymakers the required information about climate. And somehow the data in this case are provided at the European scale, and they are provided as data, as multivariable data covering different timescales. I'm not going into the details because you will have a webinar specific on the operational energy service, but here I'm highlighting one of the applications that is available together with the data set. And somehow the idea is that this within this contract, the information at the climate projection timescale is given by combining together 12 different combinations of regional climate models at a high resolution with the GCMs and different scenarios. Of course, the data have been bias adjusted before extracting the relevant information. And what I would like to highlight here is the strategy that this contract is choosing with respect to composing and creating multimodals. For example, in this case, there has been developed a sub-sampling methodology that aims at favoring somehow skilled models, but at the same time preserving as much as possible the spread, that is original spread in the climate sensitivity. And of course, this depends on the different variables. I'm pretty sure you will have more information I think in the next webinar. Another different example of which we hear about right now is related to the operational water service managed by ECMWF. And actually, this service aims to give information to a broad range of water managers for the water allocation, flood management, and so on. And somehow, also in this case, the information on climate and water indicators is given at the European scale by making use of the regional climate projection. So in this case, again, a composition of different regional climate models, combination combined with the general circulations model is chosen. But here the strategy is different because in this case, there is a hydrological model, so an impact model that is run on this possible composition of regional climate models. And in this case, several ensemble members are given. Another different approach of dealing with the multimodals is related to the infrastructure domain. Of course, buildings and infrastructures are really quite vulnerable to climate change, and mostly because of their design, because let's say of their location, and somehow we can think that climate conditions and extreme events may really have a large impact on infrastructures. So somehow the way the uncertainty is provided for this set of users is instead focusing on looking at the worst case scenario. That's again a different kind of an approach. The last example that I would like to mention here related to the multimodal composition is from one specific activity that is relevant also for the tourism sector, and it's the fire risk indicator. Let's say the map in color is a snapshot of an application that is available in the climate data store. And in this case, we have the fire weather index is a risk danger indicator that tells the user the probability that a fire may be spread or sustained by meteorological conditions after the ignition has taken place. In this case, also, we have a combination of 5 different regional climate projections models and GCMs. And the multimodal composition here is instead given as the worst and the best case at the grid box level. I would like to quickly go and mention another cross-cutting activity that is related to the bias correction. So given that climate simulations are approximations of the real climate system, they include errors. And the bias correction is the process that permits to scale climate model outputs, taking into account their systematic errors. And of course, this has been done in order to improve their fitting to observations. But different methods are, of course, available, and different data sets with respect to which applied bias corrections are available. They depend on the variables, they depend a lot on the applications. And even at C3S, you will find kind of a different, quite different examples with respect to the methodology of the bias correction. I quickly move to the next topic that I want to mention briefly, and this is related to the extreme events. So extreme events is quite a common issue, and this happens across the different sectors and across the different applications. Of course, the word extreme here has many different meanings. In general, we are dealing with identifying something that is very rare, or something that it is very large or very small, or maybe something that has very high impact. And somehow those three concepts, even if they are overlapping, they are very different, the one to the other one. And when we study the extreme events, we have to take into consideration the time scale of the system itself, and at the same time, the temporal length and the spatial extent of the event we are looking at. So for example, if you are looking at slow onset events like droughts, cold spells, heat waves, or if we are looking at fast events like flooding, tropical cyclones. And in this case, data and tools have to be fit for purpose to look at extreme events. And somehow we think that, of course, the quality of the data set is itself very important in order to become a reference. And regional climate projections are becoming quite interesting also for dealing with extreme events. There is a lot of literature looking at how fit for purpose are climate projections at the regional scale with respect to the global climate projections. I think I will skip this point because we are going, I think, out of time. And I would like just to mention instead a very important point, and is the user co-design and the interaction with the user. That is somehow a very big challenge. So let's say that the concept here is related to the fact that tailored climate information may be not enough or may not be sufficient. And we need to move from the concept of a science-driven and user-informed toward a demand-driven and science-informed kind of practices. So here is just to highlight that we are trying to go, when we build applications, we go away from this view of having services that are too largely dominated by the supply side perspective, and they are focusing only on accessibility of climate data. Just to make an example, when we think of meteorological, seasonal, and multi-decadal timescales, from a scientific point of view, those are very well separated timescales, but not for the user. And if you will have the possibility to follow the next webinar, where the energy service will be presented, for that kind of service, we are offering information at 3 different timescales, but those are presented to the user as if they were a unique kind of point of view. And the second point that I would like to highlight is related to the decision making that is somehow more concerned with the potential impacts and risks, and somehow the way we need to deal with the data in order to reduce the risks. This is much more interesting for the users than having to deal with the raw data or even transformed climate data. And the last point is that many users are less interested in long-term climate change than in managing short-term goals. And those are somehow instead linked to long-term factors such as the resilience to extreme events. I would like to conclude these slides with the outlook and challenges. And the first point relates to the observations, because we have seen that there is evidence that multimodal average compares more favorably to observations than when we look at a single model. And so observations are used to evaluate and also to bias adjust the models. So reanalysis and station data are the ones that are the most used kind of observations, but also observations exhibit some kind of biases. For example, for certain variables like temperature, these biases are quite small, but for other variables, they may be quite important. And one important issue is that if we think of reanalysis, even reanalysis are models somehow that are run, of course, at a much higher resolution than the climate projections, but at the global scales, but somehow the results are for some variables, some parameterization are still impacting the result and the output of the reanalysis themselves. So when we have bias in the observations, this imply that somehow this would appear as an error, as a model error that is persistent at all and across all the timescales. This is an example and just a quick view of the data in the climate data store that is the most used for bias adjusting and for and also for, let's say, evaluating the models. We are talking about the ERA 5 global reanalysis, the ERA 5 land, that is the dynamical downscaling to 9 kilometers, EOPS, daily gridded land only observation data set over Europe, and bias corrected ERA 5 data. So it is important to mention that in the plans, in the climate data store, we have to publish and to focus on new kind of regional reanalysis that may be quite relevant for this community. And so here we are talking about the European domain regional reanalysis, but also Arctic domain reanalysis. Okay, the last slide is this one. So the final 2 points is that I would like to focus on the fact that it would be important in the next phase to explore other opportunities, such as how to compose models differently, preparing multimodal, multi-scenarios, and even multi-domain analysis of regional climate projections. There is a nice work focuses on the Mediterranean area. But if we give access to new opportunities, this comes with a price. And actually, all these new opportunities have to be proper tailored, and guidance has to be given to our users. Otherwise, this information would not serve the needs of decision makers. And I thank you for your attention.